Hello, everyone. So this talk will be about online agnostic boosting. I'm Xingyi Chen from Princeton University and Google AI Princeton. And this is joint work with Natalie Brukham, Elad Hazan, and Shai Moran. Boosting is a very general methodology for combining weak learners to construct strong learners. We can think of weak learners as rules of thumb predictors that are simple to implement and simple to understand. On the other hand, the boosting framework also captures ways to improve the performance of complicated systems, such as neural networks. We might not have formal guarantees for these systems, but the boosting framework can still allow us to improve their performance in a theoretically sound way. The framework of boosting goes as the following. Suppose we have access to weak learners that give us suboptimal hypotheses from a given hypothesis class H. How can we construct a strong learner that competes with the best hypothesis in this class H? There are roughly two different settings. The first one is the realizable setting, where we assume that H has a perfect hypothesis, that this hypothesis is correct on all data. Most of the theory is known in this setting. For example, AdaBoost is an algorithm in this setting. But this, in general, is not very realistic, because if our data comes from the natural world, it's unclear, given a function class, if there is a perfect hypothesis that would be correct on all the data. And the other setting is the agnostic setting, where we don't assume that there is a perfect hypothesis, and we just compete with the best hypothesis in the hypothesis class H. We'll also consider the online boosting setting, where we receive data at each iteration and we update our hypothesis iteratively. This is more general than the batch setting, and it has applications in time series prediction and also control. For example, online boosting of dynamical systems is a work in this area by Agarwal, Brukham, Hazan, and Wu. The agnostic boosting problem has been studied in the offline setting by Kalai, Kanade, and Feldman. However, it's unclear how to adapt their algorithm to work in the online setting. The online boosting problem has been studied in the realizable setting by Begelsheimer, Kalai, and Luo. And in this work, we propose an efficient method for online agnostic boosting. We also draw inspiration from online gradient boosting. I will first introduce the online classification setting. Suppose we have binary labels plus minus 1, and we receive xt at each iteration, and we try to predict the label, and we suffer a loss. We use the online correlation as the metric to benchmark the performance of a hypothesis. And it's defined as the correlation over time with the data that we receive over t iterations. And we define the best hypothesis as H star as the hypothesis in the class that has the maximum online correlation. And in the boosting problem, we have access to gamma approximate online agnostic weak learners. So these are online learning algorithms that output hypotheses at each iteration upon receiving a data point xt. So they output the YT hats. And their average correlation is up to gamma times the maximum correlation of a hypothesis in a hypothesis class H minus an average regret term. This is a very permissive assumption because gamma is less than 1, so they can be rather weak. And note that these agnostic weak learners have this guarantee not only on the original labels Y, but also if you relabel them, this guarantee will still hold. And our goal is to output a sequence of aggregated hypotheses, H1 through HT, at each iteration, such that their correlation is competitive with H star up to additive error epsilon. So with our algorithm, we propose an algorithm such that with O of 1 over epsilon naught squared, gamma squared weak learners, it outputs aggregated hypothesis HT such that the average performance is greater than or equal to the online correlation of H star minus an average regret term scaled by 1 over gamma minus epsilon naught. So if we want a better accuracy, we will need more weak learners. The algorithm works in the following way. Let A1 to AN be the weak learners we have access to, and big T to be the time horizon, and epsilon naught to be the accuracy parameter. At each iteration, we receive a data xt, and we produce H alpha T, which is a combined prediction from all the weak learners. We will use the Frank-Wolf method to do it, and I will explain further this step. And then we predict YT hat, which is a clipped version of this predictor, this combined predictor, because at this point, this H alpha T might produce a prediction that's outside of the range of -1 and 1. And then we receive an online reward FT alpha T, which is the approximate correlation function. And in the end, we pass a relabeled XT YTI to each of the online weak learners. And note that the label is different for each weak learner. This is analogous to the online gradient boosting algorithm. And because these weak learners are online learners, that they take data and labels at each iteration. So the main technique that we use is the Frank-Wolf algorithm with an approximate oracle at each time step. The Frank-Wolf algorithm has been studied for many years in optimization, and we have formal guarantees for this algorithm. We use the Frank-Wolf algorithm to optimize an approximate correlation function, and this is what I mean by the approximate oracle. So instead of optimizing over the exact correlation function, we optimize over FT alpha instead, where alpha defines a linear combination of all hypotheses. And FT alpha is 1 minus the absolute value, the smooth absolute value between the combined hypothesis and the true label. And the Frank-Wolf algorithm works as in the following way. So suppose we have seen I weak learners and we're at alpha I. We take the gradient of FT with respect to alpha I, and we find the vertex in the polytope that has the maximum inner product with the gradient VI, and we move towards that direction. So in the approximate oracle, we instead optimize over an enlarged space, and we can actually use the weak learner to obtain this vertex in the enlarged polytope, and this is how we use the weak learner to construct the strong learner. So the idea of Frank-Wolf is that the weak learners, suppose we're at weak learner I, and it should be able to do well on the residual of the weak learners before weak learner I. So the Frank-Wolf algorithm can help us to do that. And this is just a schematic of how this algorithm would work. So at each iteration T, we run the Frank-Wolf algorithm over all the n weak learners, and we produce a prediction at the end after having used all the weak learners. So at each iteration, we'll output a prediction, and over time, these predictions are the output output from the yellow box that you see here. So some of the future directions that we're interested in include a framework that unify the agnostic and realizable boosting analyses, because the analysis in realizable boosting focuses on reweighting examples, whereas in agnostic boosting, it focuses on relabeling. And we're also interested in tighter lower bounds for agnostic boosting and also the empirical performance of our algorithm. Thank you.